In this video, we are going to continue looking at the different laws of probability. In the last video, we looked at the first 5. In this video, we're going to, I think, get 3 more in. All right. Before we do that, we're going to talk about a kind of characteristic that events can have, kind of a way of defining a relationship between these characteristics, or between these events. And this is mutual exclusivity. All right, so if 2 events are mutually exclusive or have mutual exclusivity, all right, then it means that the events don't share any common points. Or probably a better thing to say instead of points would be outcomes. All right, so they share no common outcomes. If we wanted to look at this graphically, like we have done with some of our other concepts, in this case, this is what it would look like. All right, we would have the event A in purple and event B in blue. All right, there is no overlap. There's no connection. There are no outcomes in common. They don't share any common outcomes. All right, so that's what mutual exclusivity is. Right, so now we're going to use this to look at some more laws of probability. All right, so we're going to look at the 6th law. All right, and it says that if our events A and B are mutually exclusive, then we can calculate the probability of the union of A and B as the probability of A plus the probability of B. All right, so this only works if our events are mutually exclusive. If they're not mutually exclusive, then this is not how we would calculate the probability of a union. We'll look at that in just a moment. All right, but that is our 6th law. Now let's go ahead and just take a look at this in practice. All right, so once again, we're going to go with our example, our experiment of drawing a card from a deck of playing cards. And the question we're going to ask this time is, what is the probability of drawing, let's see what my actual example is before I write that down, of drawing a club, a red card, or both. All right, so one thing that we might ask ourselves just right off the bat is, are these events mutually exclusive? Right? Are there any cards that is Balder? All right, we're just going to keep going despite my Sheltie acting a fool. All right, so do we have a card that is both a club and red? All right, if you're not familiar with cards, you might not know this, but the answer is no. There are no cards that are both red and clubs. All right, so the clubs are one of the black suits. All right, and so there are no cards that are red and a club. All right, and so we can go ahead and calculate our probability using our 6th law of probability. All right, so we're looking at the probability of drawing a club. All right, drawing a red card, or both. All right, so once again, we're going to have our P, our probability statement. Inside the parentheses, we're going to put whatever the event is we're looking for. In this case, it's the union of club and red. We know this because we're asking of drawing either card or both cards, right? So this can be calculated as the probability of drawing a club plus the probability of drawing a red card. All right, so starting with the club, or actually let me just write that out real quick. So let's say, so this is equal to the probability of drawing a club plus the probability of drawing a red card. All right, so to find the probability of a club, all right, first we need to know how many outcomes are in this event. So how many cards in a deck of cards are clubs? All right, well, it's one of the suits, so a quarter of them, and a quarter of 52 is 13. All right, so we can write 1 if we just knew that it was 0.25 or 1 over 4, we could write that, or we could write 13 over 52. Those are mathematically equivalent. And then for the red cards, again, how many cards are red? Well, it's half the deck, half is red, half is black. So half of 52 is 26. And then, of course, the denominator is 52 for both of them, because that's the number of outcomes in the sample space, right? There are 52 unique cards in a deck. All right, so the number of outcomes is 52 for the sample space. All right, so when we do this, so 13 over 52 plus 26 over 52, all right, probably are not going to be terribly surprised to find that our answer is 0.75. All right, so the probability that you will draw a card that is a club, a red card, or both is 0.75. All right, so again, this only works because these two events are mutually exclusive. If they were not mutually exclusive, we would have had to do something else. All right, so now let's move on to our next law of probability. It is related, but this is the 7th law. Once again, we're going to start with if our events A and B are mutually exclusive, then the probability of the intersection of A and B is equal to 0. All right, and this makes sense if we think about it. If we go back and we look at our diagrams, if we drew those down, of our intersection, we saw that the event is that overlapping section of those circular events, right? And we saw that with mutually exclusive events, there is no overlap, right? The circles that represent the events don't touch. So there is no overlap, so there are 0 outcomes in the event, right, of a intersection, right? And so the answer is 0, because if we divide anything, or divide 0 by anything, we're still going to get 0. Right, this one, we really don't need to do an example for, but just really quickly, if we were to use those same events from the last example, so club and red, right, and we were to look for the probability of the intersection of drawing a red club, then once again, kind of our denominator is going to be the same, right? The number of outcomes in the sample space, right? And then the number of outcomes in our event is 0, right? Because there are only black clubs, there are no red clubs, right? And so 0 over 52, that's going to give us 0. All right, now that brings us to the 8th law of probability. All right, so the 8th law of probability is similar to the 6th in that it is telling us how to calculate the probability of the union of two events. However, for the 8th law, there is no condition required, right? So this is true for any two events. All right, so for any two events, A and B, the probability of the union, actually I probably need to give myself a little bit more, just go ahead and come over here. All right, so the probability of the union of A and B is equal to the probability of A plus the probability of B. All right, so it's pretty similar to our sixth law, but here's where we have our difference. We're also going to subtract. I still didn't have enough space. Good night. All right. Well, I want this all on the same row, so I'm just going to rewrite that again. All right, so once again, probability of A plus the probability of B. All right, then we're going to subtract the probability of the intersection of A and B. All right, so that is how we're going to calculate the probability of a union for any two events. All right, so looking at this, before we actually look at an example, why are we subtracting the probability of the intersection? All right, well, if we think about what the probability of a union is looking for, right? It's looking for the probability that you draw a card from one event or the other, or from both, right? In this case, for A and B, you're looking for the probability that you draw something from event B, or, well, I guess in this case, it's not drawing, right? You're looking for an outcome in A, an outcome in B, or both, right? And when we looked at our little diagram, we colored in the entire thing, right? Both full circles and the area that overlaps. All right, well, when you're doing this, right, the probability of A plus the probability of B, right, you're taking those two full circles, right, in our kind of diagrams, and you're smashing them together, you're adding them together. All right, however, there's that bit of overlap, right? That overlap is counted in A and in B. It's counted in both of those. All right, so in order to not double count those observations in the intersection, we're just going to subtract it out, right? We're going to subtract it out once, right? So it's counted that A in B, that's counted in the circle for A and the circle for B. I'm putting my hands out too far. All right, so for A and for B, so it's counted twice. So we have to remove it out once. All right, so that's why we're going to be calculating our probabilities like this. Now let's look at an example. All right, so for this one, we're going to say, all right, what is the probability of drawing a red card, a face card, or both? All right, so if we were to see this question on a homework or a test, one of the first things that should pop into our minds is saying, well, we've got this, you know, A, B, or both. That's telling us it is a union, all right, that we're supposed to be finding the probability of a union. So now that I know that, I also need to ask, are these events mutually exclusive? Because that's going to determine whether I use the sixth law or the eighth law. All right, so I look at my events. All right, so we'll say A is red, B is face, and I say, are these mutually exclusive? Right? And the answer is no, right? So there are red face cards. There are face cards, there are red face cards and black face cards. So you are going to have some overlap. You do have an intersection. All right, so we're going to have to use that eighth law of probability. So when we go to do our calculation, we're going to say the probability of the union of red and face. That's going to be equal to the probability of drawing a red card plus the probability of drawing a face card minus the probability of the intersection of red and face. All right, so we're going to bring that down here now to finish up this calculation. So, you know, what's the probability of drawing a red card? All right, well, to know that, we're going to need to know how many red cards are there in a deck. All right, that's our numerator. That's the number of outcomes in our event, right? As we've already discussed, it is 26. Then we need the number in the sample space. That is still 52. All right, then we're going to need the probability of drawing a face card. All right, once again, we're going to need to know the number of outcomes in the sample space. In case anyone doesn't know, right, there are 3 face cards for each suit in a standard deck: the king, the queen, and the jack. Right, there are 4 suits, so if there are 3 face cards, 1 in each suit, that means 3 times 4, we have 12 face cards. All right. Once again, we're going to divide by 52, and now we're going to subtract the probability of the intersection. All right, so we need to know how many outcomes are in our event. All right, our event is the intersection of red and face, so how many red face cards are there? All right, well, if there are 12 total, and half of those are red and half of those are black, that means that there must be 6 red face cards. All right, and so we have 26 over 52 plus 12 over 52 minus 6 over 52. All right, and so that is going to give us a final answer, if I can find it, of 0.615. All right, and that is it. So that is how we, one, looked at the concept of mutually exclusive events. All right, we found out that depending on whether our events are mutually exclusive or not, we're going to have to pick one of 2 ways of calculating the probability of a union. If we don't want to pick one, just go with 8 because it works whether they're mutually exclusive or not. Because if you think about it, if the probability of the intersection of 2 events for mutually exclusive events is 0, then that last term is just going to fall off on 8. All right, but again, covered the concept of mutually exclusive events. All right, looked at how to calculate unions for both mutually exclusive and other events, as well as looked at the kind of that 7th law of probability, where we looked at the probability of the intersection of 2 mutually exclusive events. All right, but that's it for this video. In the next video, we're going to be talking about conditional probabilities, and I will see you in that video.